Suppose we slide this ball along the floor with a constant velocity of v0. Then, in the absence of acceleration in the x direction, the displacement of the ball at any time t will be v0 times t. And we apply the very same logic to find the range of the projectile. First of all, what is the range of the projectile? This is the distance r from the launch point where it started out from to the point where the projectile finally lands. And at this point, we are making the assumption that it lands along the same horizontal level. Given the initial speed of v0 and the launch angle theta, we need to find what this range would be. To solve this, we make use of two concepts that we have learnt so far. The first is that we can apply the equations of motion independently along each axis, and to find the range, we will apply this along the x-axis as we are measuring the range along the x-axis. So we completely ignore what's going on along the y-axis. The second concept that we will use is that along the x-axis, the velocity component of the projectile v0x remains unchanged throughout the flight, or along the x-axis, the velocity is constant. Since the x velocity of the projectile remains constant and there is no acceleration along the x direction, the displacement of the projectile along the x-axis will be similar to that of the ball sliding along the floor with a constant velocity. And when the projectile lands, the x displacement would give us the range of the projectile. In the absence of acceleration along this direction, the range would be the constant velocity along the x-axis times the time of flight of the projectile. The x component of the velocity always remains constant and is v0 times cos of theta. And we have to multiply this with the time of flight of the projectile. And if you remember from the previous lesson, we obtained that time of flight as 2 times v0 sine theta over g. Multiplying the two, we obtain the range of the projectile as v0 times cos of theta times 2 times v0 sine of theta over g. And we can simplify this further because 2 times sine of theta times cos of theta gives us sine of 2 theta. So we have a simplified version which is v0 squared times sine of 2 theta over g. We could also express the range in another form which for some of you may be easier to remember. It is 2 times v0x times v0y over g, where v0x is v cos theta and v0y is v sine theta. Or you could also remember it as we have in the previous step, which is v0 squared times sine of 2 theta over g. But personally, I prefer to remember it as the x component of the velocity times the time of flight, and I remember the time of flight as 2 times v0 times sine of theta over g. The choice is really yours, whatever you feel comfortable with, because they all converge to give you the same range. We now take the same problem as in the previous lesson, but this time we compute the range. In the previous lesson, we had computed the time of flight of the projectile, and in this lesson we will compute the range. So we launch the projectile with a speed of 70 meters per second and at an angle of 45 degrees, and we need to find the range of this projectile. So we are given V0 as 70 and theta as 45, and substituting this into the formula for range and assuming g to be 10 meters per second squared, we obtain the range as 490 meters. So the range of the projectile is also dependent on the initial launch speed and the launch angle. But as far as the launch angle is concerned, it is quite clear that in order to maximize the range or throw it furthest for the same speed, the launch angle would have to be 45 degrees. That way, sine of 2 theta would be 1 and the range would be maximized. But more on this in the next lesson. The greater the speed we throw the projectile with, the greater will be the range of the projectile. In order to obtain the maximum range for a given initial speed, we would have to launch the projectile at 45 degrees.